Living in California, we're familiar with a few things. Smoggy days and traffic jams and technology breakthroughs that lead to the need to plug in more gadgets. But where does all this energy come from? Well, luckily in California, we also see a lot of something else, sun. And solar energy can give us the traffic jams without the smog and the ability to power our new lightweight devices without increasing our electricity bill. But chances are most of you have already heard of solar energy. So what has prevented you from not already making the switch? Was it the high upfront cost or the inadequate space for the current flat, rigid silicon solar cells on the market today? Well, what many of you may not know is that there is an emerging nanofilm material solution called perovskite that addresses both of these two issues. Perovskite is a cheaper, more flexible alternative to silicon and doesn't need a flat place for installation, but instead can be spray coated to wrap around telephone poles or be molded to a variety of other shapes. And in the past few years, perovskite efficiencies have skyrocketed. While it took silicon, shown in blue, over a decade to reach 20% efficiency, perovskite reached similar efficiencies in a matter of years, making it the fastest advancing solar technology in history. But in order to keep perovskite efficiencies on the rise, more optical properties of this relatively recently discovered novel material need to be better understood. The problem is that we're working with nanofilms, which are too thin to directly measure what's happening to light inside. This is where my work as a mathematician comes in. I receive data from a physics group on campus on things that can be measured, such as the amount of light entering and exiting the material. I then take this data to the computer at my office desk, and I create a mathematical model to fill in the gaps. My model incorporates properties of the material that we already know, such as photoluminescence, meaning that perovskite absorbs and re-emits photons of light. But it provides more information as well, such as the number of absorption and emission occurrences and the amount of thermal or heat losses. It also describes the amount of scattering or light lost back through the top surface of the material, and ultimately the amount of light collected at the edge. My work informs other researchers in the field and pushes manufacturers one step closer to getting perovskite solar devices on the market. So the next time that you hear about the global energy crisis, the need for clean energy, or even look at your own electricity bill, remember perovskite as the emerging solar solution of tomorrow. Thank you.